Okay, so hello. My name is Jesus da Pena. I'm a specialist in biomechanics. I am originally from Spain, but all my professional life has been in the United States. I am now a retired professor at Indiana University. In my university job, I did a lot of research on sport biomechanics, and my main area of work was the high jump, but I also did research on the discus throw. Between 1994 and 1996, I did a research project on the discus throw for USA Track and Field, which, as you know, is the equivalent of FIDAL for the United States. And in that project, I filmed with two cameras simultaneously the top American discus throwers at two major competitions. Then I made a 3D, three-dimensional analysis of the athletes' movements. And after that, I wrote reports for the discus throwers and their coaches, explaining what I thought that the athletes were doing right in their technique and what I thought they were doing wrong. In this Zoom presentation, I will explain the basic mechanics of discus throwing technique. Okay, you can download copies of my two written discus throw reports for USA Track and Field in this webpage that you see there. There's a men's discus throw report and a women's discus throw report, and they are the number 3 and number 4 items from that webpage, counting from the bottom. Number 3 and number 4, these are the discus throw reports. And also, FIDAL will tell you how to download the recording of the present talk. And in fact, that recording will give you more time to write the details of that webpage, because you did not have enough time to write it down, I'm sure. Okay, so here is the discus thrower at the time of release. And the result of the throw is going to be determined almost completely by the speed of the discus at release. So we have a velocity of the discus, and that velocity or speed of the discus, we can break it down into two components. There's a horizontal velocity component and a vertical velocity component. And the throwers that I analyzed were on average somewhere between 55 and 60 meters. At typical speeds at release will be about 24 meters per second for the total speed, roughly. The horizontal is about 19, and the vertical is about 14. And this angle here, from the velocity and the horizontal, this is about 35 degrees. Okay, so now I'm going to make an analogy between our discus thrower and a battleship. And let's say that the ship fires its cannon, and the speed of the projectile relative to the ship is about 3,000 kilometers per hour. That is, if the ship is anchored, if it's stopped, this is the speed of the projectile. But let's say now that the ship is traveling forward. Okay, so now the ship has a forward speed of, let's say, 60 kilometers per hour. In that case, the speed of the projectile relative to the ship is 3,000 kilometers per hour, but relative to the still water or relative to the land, it's the sum of 3,000 kilometers per hour plus 60. So it's not a big improvement, but it is a little bit more speed when the ship is traveling forward when it shoots the cannon. So the ship is a shooting platform in the same way our discus thrower is a throwing platform. So in the same way, if at the time that the discus is released, if the thrower is moving horizontally in the direction of the discus and vertically also up in the direction of the discus, this will help to increase the total speed of the discus. both in the horizontal direction and in the vertical direction. So because of that, it's good for the thrower to move horizontally across the throwing circle, and the thrower will do that. And also later on, there will be an upward linear velocity of the body that will help with the vertical velocity of the discus. Okay, so now we're going to see a throw. We're going to see it's going to repeat 3 times. So we see the thrower starts and then drives across the circle and then goes up.
Vediamo il lanciatore che si carica, ruota sulla pedana e poi si solleva leggermente.
So horizontal movement here.
Un movimento orizzontale in questa fase.
Vertical.
Un movimento verticale nella successiva.
Okay, so the forward velocity of the body is going to add to this horizontal speed of the discus. The upward linear velocity is going to add to the vertical speed of the discus. Well, the forward velocity of the body contributes about 6% of the horizontal speed of the discus at release. And the vertical speed of the body provides about 10% of the vertical velocity of the discus at release. So horizontal and vertical translations of the body, the throwing platform, the ship, they provide additional speed for the discus, so they are a good thing. But they account only from between 6 and 10% of the final speed of the discus. So the remaining 90 to 94% of the final speed of the discus is determined by the speed of the discus relative to the body. And this is not produced through translation, but we will see that it's produced through rotation. So in the discus throw, rotation is much more important than translation. So we have seen that a discus thrower needs to produce some translation and a lot of rotation. And we're going to be looking at how the discus thrower does that, especially the rotation. But first, we'll have to look at some mechanical concepts. Well, the first one is not really mechanical, it's something else. It's about clockwise and counterclockwise. For most people, particularly the older people in the audience, clockwise and counterclockwise is easy. It's very intuitive. It's immediate, right? For me, clockwise is like this, and counterclockwise is like this. This is because when I was young, this is how our clocks look like, all of them. And so the older people in the audience will be totally familiar with this. It's immediate for them to understand, to perceive clockwise and counterclockwise. And some of the young ones too, but some of the young ones, their clocks look like this. So I'm sure that all of them can figure out what direction is clockwise and what is counterclockwise. The problem is they may have to think for a little bit before they, if I say, oh, this is a clockwise motion, counterclockwise, and I'm going to say that a lot, they may have to think a little bit. Oh, wait a minute, clockwise, that's the, by the time they figure that out, I've finished, I'm talking about something else. So what I propose that you do is for you to take a pen and a piece of paper and make this drawing and have it next to you while I talk. That way, when you're in doubt and I'm talking about clockwise or counterclockwise, all you have to do is, and you're ready to continue, okay? All right, so now these are mechanical concepts. The first one is center of mass. The center of mass is a point that defines the average location of all the particles that make up your body. And it's not located in any particular organ, like it's not in your liver or something like that. It is an average for the positions of all parts of your body. So if I'm standing up with my arms by my side, my center of mass is approximately in my navel. Okay, now if I raise my arms like this, part of my mass is in the same place as before, but some of it, my arms, are higher. So the average of my whole body is a little bit higher. So my center of mass goes a little bit up from my navel. Right, the second concept is force. Force is defined as the action of one object on another. So when object number one makes a force on object number two, a force this way, object number two accelerates in the direction of the force. You'll have an acceleration in that direction. Okay, the next concept is action and reaction. So if one object makes a force on another object, like this, the second object makes on the first object an equal and opposite force. The way an object is going to move will depend on the forces that are received by the object. So, for example, if I had a wall in front of me, a wall, and then I pushed against this wall very hard, then I would move this. I would move the whole world that way. You will not notice it because the mass of the whole world and the wall is huge, but I would be actually accelerating the whole world in that direction, just a tiny bit. So the rest of the world will move that way, but just with a very small acceleration, but it will move. So while I push on the wall that way, the wall pushes on me this way. So as I push against this wall, I find that my body will move backward because I'm receiving a force and my mass is very small compared with the whole world, of course. Okay, so now we're going to see that force not only produces a translation, as I have explained, but it can also produce rotation. All right, so I'm going to show you 3 videos with 3 different forces that I'm going to be making, 3 different situations. And the first one, I'm going to be pushing this book through the middle of the book. So, oops. I'm going to be making a force through the middle of the book. And this force, this point here, is roughly the position of the center of mass of the book. All right, so let's see that. That will produce a translation. A force through the center of mass produces a simple translation. Okay?
Una traslocazione, diremmo.
Okay, so now we're going to see the second example in which I'm going to be making a force, but it's going to be made a little bit to the right. I call it an off-center force because it does not point through the center of mass. It points through the side. And what we're going to see is it's a force upward in your screen. So the center of mass is going to translate upward, but also we will see that the book will rotate around its center of mass. So this produces a translation plus a rotation. Okay, now the third example, I'm going to be making something called a couple. And this is like, I mean, a couple can be 2 things, right? 2 eyes, 2 ears, 2 hands. But in mechanics, a couple has a very specific meaning. A couple is defined as 2 forces that are equal and opposite, and they have different lines of action. So, for example, if I'm making a force like this, well, that's not a couple, it's just 1 force. If I have 2 forces like this and they're equal and opposite in size, it also is not a couple because they have the same line of action. But if I have this, then I have a couple. Or if I'm like this, that's also a couple. Okay, so these are the 2 forces I'm going to be making on the book. So the total force is how much? It's 0, right? Like the force on the right, maybe 100 newtons up, the force on the left may be 100 newtons down, and the total force is 100 minus 100 is 0. So the center of mass is not going to go anywhere. But the two forces are going to be producing a rotation. Okay? So let's look at this again now in a slightly different way. We see the same three examples. So a force through the center has a line of action that passes through the center of mass. And this is the cause for the movement. And this is the effect. We have a pure translation. So now we're going to have an off-center force. And this is the line of action. You can see that there's a distance between the center of mass and the line of action. And this is called the moment arm of the force. And the result is a translation plus a rotation. Okay, so now I'm going to be making a couple. We're going to look first at the force on the right side. We'll call it force number 1. So it has a line of action number 1. And it has a moment arm. And then the other force has a different line of action, and it also is off center. And the result here is a pure rotation. So with a force through the center, there's no rotation. An off-center force produces counterclockwise rotation in this example, and a translation. And in this other case here, we have a pure rotation. So the tendency for rotation depends on two factors. Number one, it depends on the length of the moment arm, and it also depends on the size of the force. So if you make a force of, let's say, 100 newtons, but you make that force 10 centimeters from the center, you get a certain tendency for rotation. But if you make that force 20 centimeters off center, you have twice as much tendency for rotation. So the tendency for rotation depends on the moment arm and on the force, and the product of these two things is called the torque. Okay, so the thing is that the torque you make on this object does not completely determine the rotation. It's necessary to make that torque for a certain amount of time. And we're going to see this in this video. So I'm going to show you two videos. In the first one, I'm going to take this chair and I'm going to make a force on it in this direction. And the center of mass of the chair is somewhere around here. So if you see it from above, I'm obviously making a clockwise torque, right? So I'm going to make this force for a very short time, and you'll see that the chair gets a little bit of speed, but it does not rotate very fast.
Applicherò questa forza per un piccolissimo periodo di tempo e vedrete che la sedia ruoterà, ma non molto.
3 times. Okay, so now we're going to see a different video. In this video, what I'm going to do is I'm going to make about the same amount of torque, but I'm going to keep it up for a longer time. So I'm going to be making a force like this, just like before. Here's the center of mass of the chair, more or less. Clockwise torque. But then I'm going to be pushing it, and then as this handle of the chair, as it moves around to here, I'll keep pushing it with a force like this. And when it comes around to this side, I'll keep pushing it in this direction. Clockwise torque, clockwise torque, clockwise torque. And then when it gets to this point, I will be pushing it in this direction. So again, more clockwise torque. I'll make the same torque, but over a turn and a half of the chair. What you'll see is the speed of rotation of the chair is going to be much larger at the end of my push. Okay, more time, more faster rotation at the end.
Quindi applicazione della forza per un maggior tempo, maggior velocità della rotazione.
Okay, so we want a moment arm, big one. We want force, big one. And we want time, big one. Okay, so you have torque and time, and torque multiplied by time, it has a name. It produces something called angular momentum. And angular momentum, you can think of it as a mechanical factor that makes things rotate. If you have a lot of angular momentum, your tendency is to rotate fast. If you have very little angular momentum, tendency is to rotate slower. But angular momentum does not completely determine the speed of rotation. There's another factor called the moment of inertia. And the moment of inertia describes how spread out an object or a person is with respect to the axis of rotation. So we're talking about rotation about a vertical axis. If I'm like this, my arms are far from the center axis of rotation, so I have a big moment of inertia. But if I do this, my moment of inertia becomes smaller. So for a given amount of angular momentum, you can decide, I want to rotate slow or I want to rotate fast. With a given angular momentum, if the moment of inertia is big, slow rotation. If it's small, fast rotation. Okay, so we're going to see another video here. Okay, in this video, we have a person sitting on a turntable. The turntable is it's a piece of wood that is on top of a wheel. So the piece of wood is free to rotate. So this other person here is going to push on this arm that way, just like what I did with the chair. So the person that is sitting on the turntable is going to get a clockwise torque over a certain time, and the person is going to get angular momentum clockwise. And so once this hand stops contact with the other person, then angular momentum will stay constant. But the person who is on the turntable will get the arms closer to the middle and he will rotate faster. And then he will take him out again, he will rotate slower again. Okay, fast rotation, slow rotation. One more time.
Rotazione più veloce con le braccia raccolte, più lenta con le braccia larghe.
So the third time, it's slow rotation, slow, fast, 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 slow rotation again. Okay, so we have that. Our person is going to receive a torque over a certain amount of time, and that will produce angular momentum. And then the person can play with a moment of inertia to adjust the amount of speed, the speed of rotation. So to a certain extent, the person can play with his or her speed of rotation, even if angular momentum stays the same. Okay, so enough mechanics. We're going to the discus. And the discus throw has 5 phases. And the phases depends on whether you have 2 feet on the ground or 1 foot on the ground, or if you're off the ground. So we're going to see a throw is going to be repeated 3 times. And what I want you to look at, he's going to be throwing away from us. And I want you to look at the feet. So at first, he'll be in contact with the ground with both legs. Both feet are in contact with the ground right now. Then he'll be only in single foot support over his left foot. And then he'll be in the air for a little bit, phase number 3. Then the right foot would land, stage 4, phase 4. And then finally, the left foot will be planted in the front of the circle. And that'll be the last phase. Okay, let's just see the throw 3 times. Just look at the feet.
Guardiamo 3 volte il lancio e controllate i piedi.
So double support,
Doppio supporto dei piedi a terra,
single support, airborne,
singolo, aria, singolo, doppio.
So 2, 1, 0, 1, and 2. Okay, so let's see the first double support phase.
Guardiamo la prima fase, quella con il doppio appoggio dei piedi a terra.
So then now the right foot is going to leave the ground. Of course, the left foot will stay in contact with the ground. And then you will take off from the ground.
A questo punto ci sarà un distacco dal suolo.
Then the right foot is going to land.
Alla fase di volo seguirà il piede destro che è a terra.
And then the left foot is going to be touching the ground. And then the last phase, both feet will be in contact with the ground. Okay, so this is difficult to find a name for this last phase. I call it the double support delivery phase. But it's not a good name because, as you can see, it's not double support. For this individual, he's got only one foot in contact with the ground. By the way, this is the time of release here. It looks like the discus is away from the hand, but my computer graphics are not perfect. They show a hand like this, not like this.
Questa è la fase di rilascio, vedete il disco che è lontano dalla mano, ma i miei grafici non sono stati precisi perché si vede un pugno, invece dovremmo vedere la mano aperta.
Okay, so that's how the hand really is at the time. So some throwers, at the time of release, they still have both feet in contact with the ground. Some other throwers have one foot in contact with the ground, sometimes the right foot, sometimes the left foot. And some throwers are off the ground completely at release. Okay, so in this case, obviously, he's on single foot on the right foot. So I still call it the double support delivery because most of this period is in double support. Just at the end, it can vary. Maybe double support, single support, or no support at the end. Okay, so I'm going to be talking now about how to generate the horizontal speed of the discus. And I'm not going to complete this topic. I will complete this topic of generating horizontal speed in talk number 2. And in talk number 2, I will also talk about generating vertical velocity, which is a much shorter discussion. So this is for the generation of horizontal speed of the discus, it's obviously important to have a counterclockwise rotation as viewed from above. So you can see that this rotation like this helps to produce this velocity of the discus. So normally, so this rotation, counterclockwise seen from above, is normally called, is produced by the z angular momentum. And that's because normally when you analyze things in biomechanics, you need to set up a reference frame. And the reference frame normally looks like this. And this third axis is the z-axis. That circle with the dot represents like the tip of the arrow pointing towards us. So this angular momentum that is useful for producing horizontal speed, we call it the z angular momentum because it represents rotations about a vertical axis, which is this, what we call the z-axis. So you will want to get from the ground counterclockwise angular momentum about the z-axis. And initially, that angular momentum that you're getting, and we will see that you get it from the ground, because to obtain angular momentum, you need a force made on you the only thing in contact with the system made by you plus the discus is the ground. So all angular momentum has to come from forces made by the ground on the thrower. And initially, that angular momentum will go mainly into the body of the thrower. It's not going to go into the discus. Primarily on the body of the thrower, a little bit will go into the discus immediately, but most of it will be in the body of the thrower.
Per la maggior
And later on in the throw, you will want to transmit as much as possible of that angular momentum from the body of the thrower into the discus, because that is how the discus gets a large horizontal velocity. So you need to get angular momentum from the ground, and then you have to transmit it to the discus. Now, here in this process, there are two mechanical interactions. One is the interaction between the thrower and the ground. And the other one is the interaction between the thrower and the discus. So here's the sequence of what happens in the throw. Okay, the athlete starts by making on the ground a clockwise torque, clockwise. And by reaction, the ground makes on the thrower a counterclockwise torque. So this produces angular momentum counterclockwise for the system that is the combination of the thrower plus the discus. And it first goes into the thrower. The discus is not in contact with the ground. So the angular momentum goes into the body of the thrower. And the thrower passes part of that, a small amount of that, into the discus. Okay, so then by having angular momentum in the discus, this produces speed of the discus, horizontal speed of the discus. But at this point, initially, for a lot of the throw, very little is in the discus, and the speed of the discus is also small. But later on in the throw, there will be much more transmission of angular momentum from the thrower into the discus. This will produce more angular momentum, a lot of angular momentum for the discus. And this will produce a large speed for the discus also. But that happens very late in the throw. Okay, so here we're going to see a throw. And it's going to play 3 times. And on the upper left part of this graphic around here, I don't know if you can see my mouse. In the upper left part, you will see graphics. Do not pay attention to those graphics right now. We'll talk about the graphics later. Okay, here we go. Okay, so now we're going to look at the graphics. This graph here on the upper left, it shows angular momentum about the vertical axis. So it's the Z, angular momentum. The top graph, like this one here, that's the total angular momentum of the person plus the discus. The second graph, this one here, this is the angular momentum of the thrower alone. And this one down here is the angular momentum of the discus. So you see that the angular momentum of the whole system, thrower plus discus, it increases a lot, starts at 0, and it goes to a very high value. And this period here, this is the initial double support period. And this period here is the single support on the left foot. You can see that the angular momentum is produced primarily in the double support and in part in the early part of the single support. And then after that, and Americans call it look at the big picture. Don't look at little details, look at the big picture. Basically, you reach this big value, and then pretty much it stays constant. Now, this thrower is a little bit not typical, because what usually happens is that here in this final stage, which is the double support delivery, here there's another increase, a small one, about maybe 10%. So maybe like this is more typical than what you see here. So, but at this point, what I want you to think about is that the angular momentum of the whole system is produced in the initial double support and in the early part of the single support. And then it's pretty much constant the rest of the throw. Okay, the next thing I want you to look at is the fact that most of this angular momentum gets stored in the body of the thrower. So you have this curve. Very little goes into the discus. And then after that, for quite a while, the thrower angular momentum stays very roughly constant. And the discus angular momentum is also close to constant, even though there's a little bit of an increase there. Let's ignore that for a minute. And then what happens is this, during the double support delivery, and actually, this is the single support here. This is the single support on the right foot. And what you have is a loss of angular momentum of the thrower and a gain of angular momentum of the discus. So what we have here is a transmission of angular momentum from the body of the thrower into the discus. And it happens in the final double support delivery, and also to some extent in the single support over the right foot. Okay, so now the question is, well, okay, that's for this thrower, but how typical is this guy? Okay, so I have analyzed something like, very roughly, like 25 men and 17 or 18 women, something like that. And I'm going to give you the data for the men, the average for all the men. Okay, so the men start at 0, obviously. You're in the back, you've gone back like this, and you stop. Before you begin, you have 0 angular momentum, and that turns at the end to 100%. 100% is the value of the angular momentum at this time. So now we'll see how that angular momentum changes through the throw. So it goes from 0% to 78% at right foot takeoff here. And then it goes a little bit more to 90. It's because of this initial race. Then it's 90, 90, 91, and then 100 at the end. Here, this is double support here.
Yeah.
This is single support on the left foot, and there's an increase there.
Okay.
And then it stays constant while he's in the air. That it has to be that way. If you're in the air, there's no change in angular momentum.
Yep.
And then in single support over the right foot, there's no change either. It stays constant pretty much. And then this 9 or 10% increase in the end. Okay, so these are the men. So you can see that the graphic that we have here, this top of the graph, it's very standard. So now we'll see women, see if they're the same.
Vediamo se per le donne è lo stesso.
They're the same, basically. Okay, so now we're going to look at the angular momentum of the discus. And everything is going to be expressed as a percent of the total system angular momentum at release. Everything is a percent of this. So this value here is maybe, it looks like 40%, maybe 35%, something like that. Okay. Okay, so, but that's for this thrower. Now we're going to see in all the men, the average, what it does. So it goes from 0 to 7 to 7 to 8. A little bit of an increase there, 8 to 12 in the single support on the right foot, and then a big increase in double support. So again, our thrower here is very typical. So now we look at the women.
Guardiamo adesso le donne.
And it's the same pattern, 0, 6, 6, 6, 10, a little bit of an increase on right foot, single support, and then the big increase in double support. One thing you may notice is that for the men, the discus at the end has 35% of the whole angular momentum of the whole system. But the women have a smaller value, 29%. And the reason for this is that the women's discus is smaller. So men's discus is 2 kilos, women's discus is 1 kilo. And also we have to consider that the men are going to be heavier than the women. They have more mass than the women in general. So considering all of that, these numbers make perfect sense. The women and the men, the speed of the discus, not angular momentum, the speed of the discus is about the same, but the angular momentum of the discus is a smaller fraction of the total. Okay, so yes, this guy is typical. Okay, so you want to maximize the generation of angular momentum, because if you have more angular momentum, you have more angular momentum to give to the discus, and the discus will get more speed. Now, we saw that to get angular momentum, you need two factors. You need to get a torque, and you need to get that torque over a certain amount of time. So first, we're going to be looking at the time. How can you make the time be the longest possible while making a full effort? So to do this, you start the throw from a very clockwise position. So you go like this, and you go back to a very clockwise position, and then you start. So if you look at the feet, that green line shows the positions of the feet. And then if you look at the hips, of the red line, that's clockwise relative to the feet. So, and then the shoulders are clockwise relative to the hips. And the arms are a little bit clockwise relative to the shoulders. Okay, so basically what you're doing is you're making your upper body be very, very, very clockwise relative to the feet. Okay, so this will give you more time to generate angular momentum. But the other thing you have to maximize is not only the time, but the torque that you receive from the ground. So we will see this next. Okay, so we have on the left here what is happening in the double support phase, and here on the right is what is happening on the single support on the left foot. So in the double support, your left foot will push forward on the ground with this force, while your right foot will be pulling backward with this force. By reaction, the left foot will receive this force, and the right foot will receive this force. Pretty much what we have here is a couple, and this produces counterclockwise angular momentum if you exert it over a certain amount of time. So then in the single support phase, you have only one foot in contact with the ground. So that foot will be the left foot, and it will be making this force on the ground. And by reaction, the ground, here's the reaction force from the ground on the athlete. So this force, if you look at it, is an off-center force, and therefore is going to be producing two things. Number one is going to throw the thrower across the circle, so it'll make the thrower move this way. But because it's an off-center force, it also will produce a counterclockwise torque and counterclockwise angular momentum. Okay, so this is like what I did, pushing the book, is example number 2 from the book push. It was the second example I gave. And what we see here on the left, all of this was example number 3 from the book. Okay, so what you want to do is make these forces that you see here be as big as possible. How do you do that? Well, obviously, you try to make a big force. But you can use technique to make that force be a little bit bigger. Okay, so how can we use technique to make the force bigger than what you can do with a maximum effort? That's the question. Okay, so for that we have to look into muscle mechanics. a muscle, for example, I don't know, your biceps, for example, if I ask you, how strong is your biceps? And you tell me it's 1,260 newtons. You can't do that because the force a muscle can make depends on several different circumstances. And one very important circumstance is the speed of shortening or lengthening of the muscle. So let's say you have a muscle and your nervous system says, okay, get activated. The muscle tries to shorten. So the muscle tries to shorten. Sometimes it succeeds and it shortens. Sometimes it cannot. And sometimes it's actually forced to get longer while it's trying to get shorter. So for example, if you're doing arm wrestling, you know, we're going like this. So if you try to go this way, you're using the muscles that internally rotate at the shoulder joint. But if you're losing, if the other guy is stronger than you are, you're trying to go this way and your muscles are trying to do this, but you're forced to go the other way. So the muscle will lengthen while it's trying to shorten. This is called eccentric muscle conditions. So now sometimes you're doing the same thing, but the other guy is equally strong to you. So you're trying to do this, but you can't move. So the muscle is now in isometric conditions. It's trying to shorten, but is maintaining constant length. And other times you win. So your muscle is activated and you succeed in shortening. Okay, so you have eccentric, isometric, and concentric situations. And the discus throw is not much eccentric happening, so we're not going to worry about it. Isometric, yeah, there's a little bit, but mainly we're going to be looking at concentric conditions. That is, most of the actions of muscles and the discus are in concentric conditions. Slow concentric, intermediate, and fast concentric, but concentric. So concentric muscle activity is what happens when you try to shorten the muscle and you succeed in shortening the muscle. Okay, so this is an extremely important property of muscles, and I'll read it slowly. The faster the speed at which the muscle is shortening, the smaller the force that the muscle can exert. Okay, so let's think about that, because this is an extremely important property of muscle. Okay, so let's say that we have a person doing a very simple throw. It's going to be like a shot put, but it's not really a shot put. It's a person sitting on a chair with a metal ball in his hand and just doing this. So the muscle responsible for this is the triceps. Now, this whole motion will be very slow. You're trying to make this shot get a very big speed, but it's going to be slow because the shot has a lot of mass and it's very difficult to get it moving. Now we change activities, and instead of a shot, I'm going to give you an apple to put in your hand. The apple has very little mass. It's very easy to get moving. So the speed will be bigger, so that everything in the motion will be faster. And then I will ask you, okay, when you threw this and it went faster than with the shot, and I said, did you feel that you really use your triceps muscle with a lot of force? And you will say, well, not really. It didn't feel that I really stressed my triceps almost at all. So then I say, well, hey, we're trying to break the world record for the apple throw. So use that muscle, give it more speed still. So use that muscle and you try again and again, you feel like, I don't know. It feels that the apple yields too easily. It gives way too easily. And I don't have the chance to really use my muscle very well. And if we measured it, if we actually measured the force made by the triceps, it would be smaller with the apple than with the shot. So this is the property of muscle. So when the muscle is allowed to shorten very fast, like with the apple, the force is small. But when the muscle is not allowed to shorten very fast, like with the shot, the force will be bigger. And this is an extremely important property of muscles that affects what makes optimum technique. Because think about it, many sports activities involve the production of a big speed for maybe your whole body or maybe some parts of your body. So for example, if you're a sprinter, as you're moving forward and you're trying to pull backward on the ground is going away from you very quickly behind you because you're traveling forward over the ground. So you need to extend your leg backward very quickly. So your foot has to be moving backward very fast. If you're looking at a high jumper, again, you want your whole body to go upward very fast. That means that your foot is moving down relative to your hip during the takeoff. So the foot is moving down very fast. So you have a fast motion, in this case, of the foot relative to the hip. And in a throw, in a shot put or a discus throw, your hand, which has the shot or the discus in it, it has to be moving very fast too. Many muscles have to be activated while they're shortening very fast. And these are weak conditions for the muscle. So the trick for good technique, or one of the most important tricks for good technique, is while some parts of the body are moving very fast, how can you move in such a way that the muscles are shortening relatively slowly? So for some parts of the body, have to be moving fast because that's the goal, that's the purpose of the activity. But at the same time, you like your muscles, or some of your muscles, the critical muscles, to be shortening slow. So let's see how this affects technique in the discus. Okay, so we're going to see, this is going to be just the initial double support in the back of the circle. And what I want you to do is look at the motion of the hips. The hips start in this position, and it's going to repeat 3 times, and just look what the hips do. They're going to rotate counterclockwise. And the feet, of course, don't move. They're on the ground. This is the double support phase. Okay, so look at the hips. Clearly fast counterclockwise motion. Of the hips. Okay. All right, so let's take a look. What are you trying to do here? The thrower is going to be pushing on the ground in this direction, right? So here's our thrower. Let me get a little bit farther away. Here's our thrower, and our thrower relative to the hips. This is the left leg and the foot, and is going to move this way. It's going to move, and the hip joint is going to have hip flexion and also adduction. Okay, so relative to the left hip joint, the foot is moving that way. So the muscles that produce that motion, the muscles that ultimately are going to be making the foot make this force on the ground, those muscles will be in concentric conditions. So the faster that the hips are rotating counterclockwise, the faster the muscles, the hip flexors and hip adductors, the faster their concentric conditions will be. So what we would like is for the hip to rotate counterclockwise, not so fast. But we are generating angular momentum. You have generated counterclockwise angular momentum in the earlier part of the double support phase, and you have a lot of counterclockwise angular momentum. How can you prevent the hips from rotating counterclockwise fast if you also have a lot of angular momentum in your body? Well, first trick, you keep your arms spread out. If you're like this with the arms very far, like that, then your moment of inertia is big. So with the angular momentum you're getting, the whole body rotates more slowly than if the arms were flexed or semi-flexed. So for maximum angular momentum, you're getting minimum or reduced hip angular velocity. So let's see this in this animation. Just look at the fact that the arms are spread out all the time.
Quindi controllate, fate attenzione a come le braccia durante tutto il gesto siano molto allargate.
Okay, so by doing that, you are facilitating, you're making the muscles, the hip flexors and the adductors of the left leg be in slower concentric conditions. And this helps the muscles to make a larger force and the foot to make a larger force on the ground. And that's very good. You could make the same discussion for the other foot. The other foot is trying to pull backward. And here you'll have the hip extensors. Okay, so you have the hip extensors and adductors also. So by having the hips have a slower angular velocity, by keeping the arms spread out, that makes the muscles of the right leg also be in slower concentric, so you can maximize this force. Okay, trick number 2. Actively throw your shoulders and your left arm counterclockwise. So how does that work? Well, the ground is giving you angular momentum. So your body has all this angular momentum. And you can choose, by using your muscles, you can choose if you want to put that angular momentum into your upper body or into your lower body. So the athlete, if you do, this is the lower body, this is the upper body. If you use the muscles of your trunk to do this, okay? This is the oblique muscles of the trunk. By doing that, you're putting more angular momentum into your upper body and leaves less angular momentum for your lower body, which makes the hips rotate more slowly. And this also allows you to make a bigger force with your feet against the ground. Okay, so let's see. You will see that the shoulder is kind of hard to see in this view, but the shoulders are going to rotate counterclockwise faster than the hips. It's not easy to see in this view, but believe me, it happens.
Non è semplice da vedere con questa visualizzazione, ma credetemi.
So remember that initially the shoulders are very clockwise relative to the hip. So here the shoulders will almost catch up with the hips. Okay, so now let's see the single support phase. And in this phase, again, you want to maximize this force. And the discussion for the left leg is the same as before, is if your hips are prevented from rotating fast, your leg muscles will be in slower concentric conditions. Okay, so what are you doing? Well, you're keeping your arms spread out just like before, but also now the right leg is off the ground now. So the right leg also is far from the vertical axis of rotation too. It won't necessarily be totally straight, but it will be close to straight. It should be. So by having the arms spread out and the leg also spread out, you have a bigger moment of inertia, so slower counterclockwise rotation of the hips, which increases the force you make on the ground. Okay, that's trick number 1, right? Remember this trick number 2. Trick number 2, so trick number 1 is stay spread out. Trick number 2 is make everything in the body except for the hips rotate counterclockwise as fast as you can make it. So not only the arms, but also now the right leg also get thrown counterclockwise. The left arm will be thrown this way. The shoulders will be thrown this way. The discus arm will also be thrown this way to some extent, but also the right leg will also go around. And as a result, the hips will rotate much more slowly, and that will increase this force. So here's an animation of that. Single support on the left foot. So at this point, the thrower plus discus system has almost all of the angular momentum that it's going to have during the throw. There's a little 10% probably in the end that you want to get, but almost all of it is already there. He's got it. It's in his body. Well, that angular momentum is almost all of it stored in the body of the thrower. The discus has very little of it. The thrower has two jobs left to do. One of them
Okay.
to obtain a little bit more angular momentum in the final double support delivery. It's a small amount, but you want it. And after that, you want to transmit as much as possible of the angular momentum from the thrower to the discus. Okay, so you have almost all of your angular momentum. You need to be ready so that later in the double support, final double support, you can get that little extra of angular momentum. And then super importantly, you want to put as much of your angular momentum, funnel it, transmit it into that discus. But that will be covered in talk number 2. Thank you. That's it.